Okay, this is going to be Lab 2, Part A, and this is kind of what we did last semester, but I'm going to update this so it reflects some changes, okay? So it'll be pretty much consistent with what we've done last semester, although there'll be some new stuff in here. Boolean and De Morgan. Now, at the end of the updated one, I'll have a slight update on that, or a very short intro on that, which we'll go deeper into too when we go into the next chapter. Okay, so let's get going with this. This is going to just be a review of what the lab will look like, but again, we're going to update this. Okay. So again, the foundation of this whole lab is just the how these will evolve into combinatorial circuits and ultimately sequential circuits as well. So this is our basic gates, and you've learned a little bit about truth tables from the lectures, and you played around with NOR, NAND, exclusive OR, exclusive NOR. The key thing you want to go back to is look at the data sheets for each of these devices and understand where these pins are, power pins and input to the various gates. And in a typical package, you'll have maybe 4 gates in one integrated circuit package, okay? If you're going to use CMOS, you want to kind of use these directions here, okay? They're a little bit different than TTL, but pretty much the same, okay? But the voltage levels are going to be slightly different. But I'll let you guys just use TTL for now, and then we'll go back to CMOS in some other lab as well. Or maybe we'll do that when we do the DC and AC lab. So I think in the updated lab, I'll create the tables for you. Right now, I had the students from last semester do their own tables for each of the gates. It's pretty straightforward. You can do that in Excel. Okay, so you'll have your, you're going to build it at home. You have your trainer board. Use the logic glitches that you used in the lab 1 and the LEDs as indicators. So whatever gate you choose, you could choose, this will be your choice, but again, cover the ones that we did, fundamentally, okay? And you'll connect the 1A and the 1B to your logic switches. And this will be cascaded. So for example, you have 1A, 1B, 1Y for this package, and you'll use the same connectivity for all of these, okay? That way you'll get them all done at one time. And later on in this lab, you'll see how easy this is to connect. Part 2, you'll be using a function generator and an oscilloscope. Now for those folks that are doing home labs, on this part, I believe your trainer does have it does. It has a function generator, but it does have no scope. But some students may have purchased the scopes. That'll be pretty fun to play around with. Other than that, you will have to do this in MultiSim for the home, for the students that are doing this at home, okay? Again, this should be pretty straightforward. You're just cascading these and applying these logic signals to all the inputs of these different gates, okay? And then for this, you'll have different outputs. You'll have, for this gate up here, you'll have 1Y, and where's this guy at? This is a 2, this is a 1Y on this side. So you just got to read these packages and confirm that they are the pinouts that they are. And again, you'll need to understand where VCC is ground. So again, look at the data sheet, kind of like what you did with Lab 1, the 7493, okay? So on your trainer board, it'll kind of look like something like this. I don't think the student wired everything up yet. He was in his en route. So this could be one. Well, actually, this is a description of how you would set that up. You'd use a interactive digital, which you kind of did, or maybe not, or you could use a double throw switch here as well, and then connect your LEDs. Here you have your famous XOR gate. Now, when we talk about a duty cycle, if you remember, I drew a square wave. That square wave was a 50% duty cycle. So that just simply means the logic 1 is on for 50, and the logic 0 is are off at another 50%. Okay, so if I say, or you set up a 80% duty cycle, that would mean what? That means the output of that signal would be 80% logic 1 and 20 logic 0, or low. Okay. On the bench, you'll need to monitor that clock as well, and then test the static and or dynamic pulse. Now, when we say dynamic pulse, we're really referring to an AC signal. The static would be the DC. Okay. So this is something you will set up with your function generator, and your enable pin here would be a hard or a static digital input where you do your logic switch. Yeah. In here, this is clearly what this is, a 50% duty cycle. This clock oscillator set up to do a 50%, and the frequency of this guy is 1 microsecond. I'm sorry, the time. And then you take the reciprocal of that, and you'll find out what your frequency is. Okay. But again, do your do your best to play around with this frequency as well. Right now, this is a OR gate that we've used, and here you can say that the OR gate here it's going to be clocking what? Clocking the, well, actually, it's going to be outputting whatever the clock is, because this is a 1, that's a 1, so it's just, yeah, okay, so you can see that it's clearly a OR gate output. And let me go back up here, sorry, this is getting jumped off. Let's go back to the AND gate real quick. You can see again here in this case, when the clock goes low, you get a low, the enable pin stays high, and the AND gate, anytime there's a 0, as you know, the output would be 0. Okay. And again, that's the time, so maybe you can take the inverse of that or the reciprocal and solve for the frequency, as we discussed in, I think, one of the lectures. Now this is a setup in the MultiSim. This is pretty cool to set up too, but you can easily set this up in the lab as well. But if you don't have that, you should be able to monitor at least yeah, 4-channel scope. The tricky part is here, you may need well, you may have to skip this one because you'll have to incorporate another function generator, which you could do. Uh, you can have the senior lab guy help you out and do that as well. But here we're throwing in a much slower. Well, actually, this is not a representation of this, so this was set up a little differently. Okay, so same principle. Yeah. And for anybody that needs help, if they're doing this on MultiSim, just let me know. I'll help you on this as well. Okay. And this is the symbol for the oscilloscope. And again, for this this experiment, just try to set it up so you can get this. Now on the updated lab 2, we may kind of change some of that, maybe kind of simplify that a little bit. Again, this the class from last semester, they were a little bit ahead, but you know, we'll catch up. Now again, this is a word generator and a logic analyzer. This is optional. Okay, so you don't have to do that, but this is, yeah, you don't need to do this. This is what you've already learned. Now this is something you probably haven't, when you wrote out the equation for this, we didn't do this. This is going to be using 2 NAND gates, yeah. So the output of this gate is AB barred, right? And then it's input with a C, another signal here. So that's going to be barred. So the whole equation is going to be barred. Okay, so according to De Morgan, which we haven't gotten into yet, and there'll be a short appendix at the bottom of the updated lab to explain this. It's not too bad, but this will get more into Boolean algebra and how we reduce the equations as well. So let's go over this real quick. So you have 2 bars here, so 2 inversions over AB. So these cancel, meaning that they get removed, and you end up with just AB. And then this bar over C over this multiplier becomes an OR. So if this was an OR, this would turn into an AND. So right now that bar is going to make this this function an OR. And since there's a bar over C, we need to write that as C naught, okay? And again, that will make sense when we get more into this, but that's kind of the most simplest way to describe this, okay? We'll go into universal NAND gates, which should be described in the chapter 3, if I believe, and then that's really it. These are some of the gates you'll use. When I upload the updated version, we'll have this a little more kind of cleaned up and easier to follow, but we'll kind of reference some of the setups we have in here, okay? Now, you know, we've done this. This is the equation for what? An exclusive OR gate, right? Again, here we're using a word generator to generate that pattern, and then a logic analyzer to look at that. You can see the word generator generating in this case, a stream of bits here that looks like a binary 3, 3, 7, 4, so a random. These are the outputs here. You can hardly see them, but there's 1, 2, yeah. Okay. And that's it. Okay, so thank you for your time. And again,